Example 1, add 30 at an angle of 55 degrees and 10 at an angle of 170 degrees. All right. Vector addition, if you just wanted to get a basic picture of this, a vector 30 at an angle of 55, for example, is a 55-degree angle from 0. So here's 0, there's 90, 55 would be somewhere in this area, and 30 is some length, okay? We use a scale probably. I don't want to draw something 30 inches long, but maybe each inch represents 5. I don't know, something like that. So 5, 10, 15, 20, 25, 30, right? Ish. All right, so that's what a vector looks like. So you have this, if you imagine a horizontal line right here through the endpoint, the angle coming up this direction would be 55 degrees, and the vector would be a length of 30. Then we would take a second vector, 10 at an angle of 170. So here's 0, right? There's 90, there's 180, so 170 would be about right there, maybe, and 10 would be about like that. All right, so again, if I drew a horizontal line through the endpoint of that vector, and I measure around this direction 170 degrees, and the vector would be 10 long. That's what vector addition looks like, vector forces. Okay, what's having more influence on this force? Which one of these forces has more influence on which direction, whatever this thing is going?
Second one?
This 31 is, right?
Oh, okay.
30 because it's
Farthest.
longer, right? Imagine two people trying to kick the same soccer ball, right? One person's kicking with a force of 30 newtons, one person with a force of 10 newtons. The person kicking with 30's got more influence on which direction the ball goes, right? This guy's kicking it that way, almost directly to the left. This guy's kind of at this angle here, but the resultant is what we're looking for, and that's just the official name of it. The resultant is which direction and how much power the final thing is going to be going. And that's what we're attempting to find here. So we want to find out this angle and this length to determine which direction this object is going to be going once both forces have acted upon it. That's what vector addition is. If you do this in physics, which if you take physics, you'll be doing this in physics, that's how you do it in physics. You get your protractor and your ruler out, you draw things to scale, and you can measure this angle with a protractor, measure that with a ruler, and figure out how long that is, and figure out the answer just graphically, which is fine. It's a really good way of doing it. We're going to be, in algebra, we're going to be doing the mathematical way. We're going to find this using math. But know that you could draw these things to scale with a ruler and protractor, get very, very accurate as you want to be. You know, if you kind of just slop stuff on your paper, it's not going to be very accurate. But if you're really technical, really close, and measure it really well, you're going to get pretty accurate answers. All right. With that in mind, know that, again, we're looking for this angle, this length. All right. To do it mathematically, we're going to convert these to component form. Okay, component form is the IJ form. Horizontally and vertically, where do we move to get these numbers? So, if I start with vector 1, 30 at an angle of 55 degrees, and I want to get something I and something J. I'm not putting pluses and minuses in yet because my calculator can evaluate those for me. Okay, does anybody remember how to get the I part and the J part?
30 cosine 55.
Very good. To get the I part, we're going to do a cosine, so we're going to do the magnitude 30 times the cosine of the angle 55, hit equals, and we get 17.21. That's positive 17.21. To get the J part, we're going to do the same thing except we use sine. So 30 times sine of 55. Every time the magnitude and the angle are what being used, and 24.57J, that's positive, so I'm going to put plus 24.57J. So that blue vector in polar form converts to this blue vector in rectangular form. That's a better form for us for what we're doing. All right. Looking at the red vector, same deal. We have a magnitude 10 and angle 170. We want to convert to IJ form. We're going to do 10 cosine of 170 to get the I, and 10 sine of 170 to get the J. Notice the times button and the end parentheses, notice I left those off there, you still get accurate results. So the calculators you have to use, you don't have to put the times, it assumes times when you do number trig functions, assuming multiplication. And if you got no end parentheses, assuming you're done taking the trig function at that point, so you don't have to put that on there. I personally find both, and then I write them down, that's how I usually do it. So negative 9.85i plus 1.74j. So if I'm looking at your papers on a problem like this, the first step I would expect to see on your paper would be that right there, where you converted both vectors into good rectangular form, and you got both in I and j order, I first, j second, and these are like terms, these are like terms, so I can add these together, algebraically, same signs add, different signs subtract, bigger sign determines sign of answer. So, if you feel comfortable subtracting decimals, that's fine. If you want to do it on a calculator, that's fine. 17.21 minus 9.85 comes out to 7.36. And 24.57 plus 1.74, 26.31. Now getting back to the back of the book discussion, that's what the back of the book answer is going to be. They stop there. Back of the book's lazy. Okay, we don't want to be the back of the book. But that's the right answer. If I were to go 7.36 to the right and 26.31 up, that would represent that red vector I had drawn on the board a little bit ago. All right. What we want to do though is we want to convert this back to polar form. Polar form conversion is a three-step process. I would expect to see on your paper the three steps going like this. Step 1, r equals the square root of something. What's the square root of? Anybody remember?
Those two numbers squared.
Those two numbers squared and added together, right? So 7.36 squared plus 26.31 squared. To evaluate that, I would use a calculator. I'm going to use the square root button. It does a beginning parentheses there. If you have your calculator set to classic mode, math print mode, the square root looks like, square root looks like that, and then anything underneath the bar is underneath the square root. In classic mode, square root parentheses, everything you put inside the parentheses is inside. I prefer classic myself, so I tend to use that. But just know that there's two different modes on your calculator. Be comfortable with whichever mode you like to use. So anything within those parentheses is going to be square rooted. So 7.36 squared plus 26.31 squared equals. It comes out to 27.32. So that's job 1 in converting to polar form. The second step of polar form is to find a reference angle alpha. Alpha is always the inverse tangent of the absolute value, just means use positives, right? Of the second over the first number. So 26.31 on top and 7.36 on the bottom. So if I do second tan, make sure you hit the second button so it says tan negative 1. And then again, parentheses, and then we've got 26.31 divided by 7.36. Most common mistake people make on this step, they do it upside down. Okay, it's the second over the first every time. It's never anything but the second over the first. 74.37 degrees. Now the final step of conversion into polar form is dependent upon what quadrant you're in. And this is the part that messes people up the most. Okay, there's 4 specific things that could be depending on what quadrant you're in. So before I finish this problem up, let me explain why it is what it is. Because I think maybe that was something I left off the last time I dealt with this. Okay, I've got my 4 quadrants. Quadrant 1's up here, quadrant 2's over here, quadrant 3's down here, and quadrant 4's over here, right? We all know that, right? All right. So imagine that I am in a vector here that is in the first quadrant, all right? And I've got my alpha and I've got my theta. Okay, let me explain what alpha is and what theta is so everybody understands this thoroughly, because it's not that hard, but if you don't know what they represent, then it makes it more difficult to understand what's going on. Alpha, what we're finding in step 2 of this process, is the angle directly from the vector to the nearest x-axis. That's what alpha is every time. Theta is the measure from the positive x-axis, 0 degrees counterclockwise to the vector. Notice in the first quadrant, if I go from the vector to the nearest x-axis, and I go from 0 up to the vector counterclockwise, those angles are the same angle, right? So that's why in quadrant 1, the rule is theta equals alpha. Because if I measure down to here and up to there, they're exactly the same, right? If my vector lives over here in quadrant 2 somewhere, I measure alpha from the vector to the nearest x-axis. So if I'm at the vector and I go to the nearest x-axis, I'm going here, that's alpha. Theta is measured from 0 degrees counterclockwise to the vector. There's theta. Again, I'm always measuring alpha and theta exactly the same way. From vector to x-axis, from 0 counterclockwise to vector. Okay? Looking at these two angles, can everybody see very clearly here that alpha plus theta equals how much?
180.
180, right? Because again, that's 0, this is 90 up here, this is 180 over here, this is 270 down here, and this is 360 over here. Right? So this angle alpha, theta and this angle alpha together make a straight line, so they add up to 180. If I want to know what theta is in reference to alpha, theta equals 180 degrees minus alpha in that case. That's why in the second quadrant it is what it is. All right. If I slide on down to the third quadrant, again, measuring alpha and theta the same way I did the other two. Alpha is measured from the vector to the nearest x-axis, so there's alpha. Theta is measured from 0 degrees counterclockwise to the vector. Every single time I'm measuring it the same way, every single time, and I'm using that to establish rules. Okay, looking at this, theta, which is the green angle, how much is that red angle there? 180. Notice 180 added to alpha takes the same space as 1 theta, right? So in the third quadrant, theta is simply going to be 180 degrees plus alpha. And each time, how do we find theta from alpha is the question. And again, we always measure theta and alpha the same way. Finally, if I'm in the fourth quadrant, I measure alpha from the vector to the nearest x-axis. I measure theta from 0 counterclockwise to the vector. Notice that theta and alpha together make 360 degrees, right? They make a full circle. So theta plus alpha is equal to 360. So if I want to get theta in terms of alpha, theta is equal to 360 minus alpha. That's where the rules came from, and I think sometimes we know where the rules came from. It makes the rules make more sense. You don't have to memorize these facts. You just have to know that the quadrant you're in influences what theta is based on alpha's measure. There's a mathematical rule that tells you how to find alpha every time. Inverse tangent of second over first, absolute value so positive. This should always be between 0 and 90. All right, every one of those alphas went from the vector to the x-axis, right? It was always just a small little angle, acute, less than 90. Okay, so absolute value positive creates a 0 to 90 angle. Second over first gets you the right angle. All right, step 3. In this specific problem, positive puts me in the first quadrant. Okay, step 3 is where signs matter. In step 1, I squared everything. Squaring makes things positive. In step 2, I have absolute value bars, makes everything positive. Step 3 is where signs matter. Positive puts me in the first quadrant. First quadrant rule says that theta is equal to alpha. So my answer to this problem, adding these two vectors, again, the rectangular answer is here. The polar answer is, what I'm looking for, It's this magnitude with that angle, so 27.32 at an angle of 74.37 degrees. That's what I'm expecting out of you on these problems. Give me a polar answer converted correctly based on the quadrant and the values in the rectangular form.